Welcome students in the lecture series of some basic concepts of real analysis. In the previous lecture, we discussed about statement of Cauchy's convergence criteria. Now, let us start with the proof of Cauchy's convergence criteria. Look at the statement again. The statement of the Cauchy's convergence criteria is a sequence of real numbers R is convergent if and only if it is a Cauchy sequence. Let us start with the proof of Cauchy's convergence criteria. Let us suppose x is equals to xn is a convergent sequence of real numbers, and our claim is x is equals to xn must be a Cauchy sequence. As given in the statement, x is equals to xn is a convergent sequence. If x is equals to xn is a convergent sequence, then limit of xn must exist, say limit of xn is equals to x. Then by the definition of convergence of sequences of real numbers, we can say that for every epsilon greater than 0, there exists a natural number k depending upon epsilon, and in this case we choose epsilon is equals to epsilon upon 2, such that for all natural numbers n greater than or equals to k, we must have modulus of xn minus x is less than epsilon by 2. Now, if we take h is equals to k, where h is depending upon epsilon and h is a natural number, and again k is a natural number which is depending upon epsilon upon 2, and for all natural numbers n and m greater than or equals to h, we have modulus of xn minus xm is less or equals to epsilon upon 2 plus epsilon upon 2, as we discussed earlier. That means, we get modulus of xn minus xm is less than epsilon. Since epsilon greater than 0 is an arbitrary number, so we conclude that the sequence x is equals to xn is a Cauchy sequence. Now, conversely, let us assume that the sequence x is equals to xn is a Cauchy sequence. We need to prove that our sequence x is equals to xn is a convergent sequence of real numbers, that is convergent to some real numbers r. I repeat, let us suppose the sequence is a Cauchy sequence, and we need to prove that that Cauchy sequence must converge to some real number. Recall, a Cauchy sequence of real numbers is bounded, as we discussed earlier. Hence, from this result we can say that our sequence is bounded. That means, x is equals to xn is a bounded sequence of real numbers, because as given x is equals to xn is a Cauchy sequence in this statement, and according to this result a Cauchy sequence of real number is bounded. That means, the sequence x is equals to xn is a bounded sequence of real number. Now, recall the previous statement, Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem states that a bounded sequence of real numbers has a convergent subsequences. Now, using Bolzano-Weierstrass theorem, we can say that there must exist a subsequence, say x dash is equals to xnk of x is equals to xn, that converge to some real number, say x star. We shall complete the proof by showing that the sequence x is equals to xn must converge to that real number. That means, limit of x is equals to x star. Since, as given in the statement, x is equals to xn is a Cauchy sequence. So, by the definition of a Cauchy sequence, given epsilon greater than 0, there must exist a natural number h depending upon epsilon. Again, in this case, we choose our epsilon as epsilon is equals to epsilon upon 2, such that we have our equation number 1, that is modulus of xn minus xm is less than epsilon upon 2 for all natural numbers n and m greater than or equals to h, where h is depending upon epsilon. Since the subsequence x is equals to x and k converges to x star, by Bolzano-Weierstrass theorem. So, there is a natural number k greater than h belonging to the given set, and the given set is n1, n2, n3 up to so on. We get modulus of xk minus x star is strictly less than epsilon by 2. I repeat, as by the Bolzano-Weierstrass theorem, we can say that our subsequence x dash is equals to x n k converges to x star. Now, by the definition of a convergence of sequence in real numbers, we can say that there must exist a natural number k such that we have this inequality. That means modulus of x k minus x star is less than epsilon upon 2. Since k is strictly greater than or equals to h, where h is depending upon epsilon upon 2, from equation number 1 with the condition m is equals to k. Now, recall the equation number 1. Our equation number 1 is modulus of x n minus x m is less than epsilon upon 2. Now, if we take m is equals to k, we get modulus of x n minus x k is strictly less than epsilon upon 2. Say this is our equation number 2, and this inequality is only for n, and n is greater than that natural number. That means, n is greater than or equals to h for every h depending upon epsilon upon 2. Therefore, if n is greater than or equals to h, we have this equation. That means, modulus of x n minus x star. If we add or subtract x k in this equation, we get x n minus x star plus x k minus x k. If we apply triangular inequality in this, then we get our equation number 3. That means, we can say that modulus of x n minus x star is less or equals to x n minus x k plus x k minus x star. Now, substitute equation number 1 and equation number 2 in equation number 3. Again, recall equation number 2 and equation number 1. Our equation number 1 is modulus of x n minus x m is less than epsilon upon 2. Our equation number 2 is modulus of x n minus x k is less than epsilon upon 2. So, from this we get modulus of x n minus x star is less than epsilon upon 2 plus epsilon upon 2, which is equals to epsilon. That implies we get our inequality. That means, modulus of x n minus x star is less than epsilon. Since epsilon greater than 0 is an arbitrary number, we conclude that limit of x n is equals to x star. Hence, we can say that a sequence of real numbers R is convergent if and only if it is a Cauchy sequence. This result is known as Cauchy's convergence criteria. Now, the geometrical interpretation of a Cauchy's convergence criteria. The geometrical interpretation of the Cauchy's convergence theorem in the real number line is that a sequence is convergent if and only if its terms eventually become arbitrarily close to each other. I repeat, the geometric interpretation of the Cauchy's convergence criteria in the real number line is that a sequence is convergent if and only if its terms eventually become arbitrarily close to each other. That is, geometrically, this means the terms of the sequences bunch together on the number line within a shrinking neighborhood of a potential limit point. And completeness of the real number means that every such bunching together sequence is guaranteed to have a limit that is also a real number. Now, our next result is properly divergent sequences. To understand the properly divergent sequences, let us start with the basic definitions. Our first definition is, let x is equals to x n be a sequence of real numbers. We say that x is equals to x n tends to plus infinity, and we write this as limit xn is equals to plus infinity if for any real number alpha. For alpha, there must exist a natural number, say k, and this k is totally depending upon that alpha, such that we have xn is strictly greater than alpha if n is greater than or equals to k. I repeat the definition. Let x is equals to xn be a sequence of real numbers. We say that x is equals to xn tends to plus infinity, and we write this as limit of xn is equals to plus infinity if for every alpha belongs to R, there exists a number k depending upon alpha, such that for all natural numbers n greater than or equals to that k which is depending upon alpha, we must have xn is strictly greater than alpha. To understand this, let us start with the next definition. Definition is x is equals to xn be a sequence of real numbers R. We say that x is equals to xn tends to minus infinity, and we write this as limit of xn is equals to minus infinity if for every real number beta there must exist a natural number k depending only upon beta, such that we have xn is strictly less than beta for all natural numbers n greater than or equals to k, where k is depending upon beta. So, if x is equals to xn be a sequence of real numbers, we say that the sequence x is equals to xn tends to minus infinity if for every beta belongs to R, there exists a natural number k depending upon beta, such that for all natural numbers n greater than or equals to k, we have xn is strictly less than beta. Now, to understand the definition, let us start with the examples. Our first example is x is equals to 2n square. We need to show that the limit of this sequence is equals to plus infinity. If n belongs to R is given, then there exists a natural number k depending upon that natural number, such that we have k is strictly greater than n. We can generate this result by Archimedean property. So, if n belongs to any real number, then we can find a natural number greater than that real number. That means, there must exist k such that k is strictly less than n. This implies that we can say that 2n square is strictly greater than kn square, and kn square is strictly greater than or equals to k, and we can say that k is strictly greater than n by the Archimedean property for all n greater than or equals to k. As we know that we have k is strictly greater than n, and we have 2n square is strictly greater than n for all n greater than or equals to k. Therefore, we can say that limit of the sequence given as 2n square is equals to plus infinity. Another example to understand the definition, let us start with the given series sequence. Given sequence is x is equals to minus 2 to the power n. What is our claim? We need to prove that limit of minus 2 to the power n is equals to minus infinity. If n belongs to any real number is given, then again by the Archimedean property, we can find a natural number greater than that real number. So, we can say that k, which is depending upon n, is strictly greater than minus n. Now, this implies that 2 to the power n is greater than or equals to 1 plus 1 to the power n, and by Bernoulli inequality, we can write as 1 plus 1 to the power n is greater than or equals to 1 plus n, and this term is less than 1, this term is greater than 1 minus n, and we can say that 1 minus n is strictly greater than minus n. If we check this inequality, we get 2 to the power n is strictly greater than minus n for all n greater than or equals to k, where k is depending upon n. Hence, we can conclude minus 2 to the power n is strictly less than n for all n greater than or equals to k, and k is depending upon capital N. Therefore, by the definition, we can say that limit of the given sequence is minus infinity, that is limit of minus 2 to the power n is equals to infinity. Now, recall the definition again. Our definition of a properly divergent sequence is a sequence of real numbers r x is equals to x n is said to be properly divergent if we have either limit x n is equals to plus infinity or limit x n is equals to minus infinity. In either case, we can say that our given sequence is properly divergent sequence. Now, geometrical interpretation of a properly divergent sequence says that if the real number line, a properly divergent sequence is one whose terms either become arbitrarily large in the positive direction, diverge to plus infinity, or arbitrarily small in the negative direction, that is diverges towards minus infinity. The geometric interpretation is that the point of the sequence on the real number line move without bound, either off to the right positive infinity or off to the left negative infinity. For example, the sequence 1, 2, 3 up to so on diverges to positive infinity with points moving rightward, while the sequence minus 1, minus 2, minus 3, minus 4 and so on diverges to negative infinity with the points moving leftward. Now, let us start with some basic theorems related to properly divergent sequences. Our first result is a monotone sequence of real numbers r is properly divergent if and only if it is unbounded. That is, if x is equals to x n is an unbounded increasing sequence, then we have limit of x n is equals to plus infinity, as we can easily check in this case. This sequence is our unbounded increasing sequence. And the second part of the theorem is, if x is equals to x n is an unbounded decreasing sequence, then our limit must be equals to minus infinity. I repeat the statement, a monotone sequence of real numbers r is properly divergent if and only if it is unbounded. First point is, if x is equals to x n is an unbounded increasing sequence, then we must have limit of x n is equals to plus infinity. And in second case, if x is equals to x n is an unbounded decreasing sequence, then we must have limit of x n is equals to minus infinity. Let us start with the proof. Let us suppose x is equals to x n is an increasing sequence. We know that if x is equals to x n is bounded, then it is convergent. If x is equals to x n is unbounded, if it is unbounded, then for any alpha belongs to R, we must have a natural number n which is depending upon that alpha, such that x n is greater than alpha, or in other words x n where n is depending upon alpha is strictly greater than alpha. But since we have, as given in this statement, x is equals to x n is an increasing sequence, we have x n is strictly greater than alpha for all n is greater than or equals to n depending upon alpha. Since alpha is an arbitrary number, we conclude that limit of x n must be equals to plus infinity. Now, our second statement is, let x is equals to x n and y is equals to y n be two sequences of real numbers r, with the condition x n is less or equals to y n for all natural numbers n. Then we have, if limit of x n is equals to plus infinity, then we must have limit of y n is equals to plus infinity. As we can check, if limit of this sequence is plus infinity, then the limit of y n is automatically plus infinity. And in second case, if limit of y n is minus infinity, then the limit of x n must be minus infinity. As we can check here also, if limit of y n, sequence of y n is minus infinity, then the term less than y n is also minus infinity. Hence, we can say that if limit of y n is minus infinity, then limit of x n is also minus infinity. So, let us start with the proof. As given, limit of x n is equals to plus infinity. So, by the definition of properly divergent sequences, for any real number alpha, there must exist a natural number k, which is depend upon alpha, such that for all natural numbers n greater than or equals to k, where k is depending upon alpha, such that x n is strictly greater than alpha. Again I repeat, as given, limit of x n is equals to plus infinity. So, by the definition of a properly divergent sequences, we have for every alpha or every real number alpha, there must exist a natural number, say k, where k is depending upon alpha, such that for all natural numbers n greater than or equals to k, we have x n is strictly greater than alpha. Now, as given in the statement, our sequence x n is strictly less than or equals to y n. This implies that alpha is less than y n, as we can check from here, as alpha is less than x n and x n is less than y n. Hence, we can say that alpha is strictly less than y n for all natural numbers n greater than or equals to k, where k is depending upon alpha. So, alpha is arbitrary number. We can say that limit of y n is also plus infinity by the definition of properly divergent sequences. Thus, we can say that if limit of x n is equals to plus infinity, then limit of y n is also equals to minus infinity. In similar way, we can prove our second result, that is, if limit of y n is equals to minus infinity, then limit of x n is also equals to minus infinity. Now, moving towards our next result. Statement of the next result is, let x is equals to x n and y is equals to y n be two sequences of positive real numbers r, and suppose that for some L belongings to R with L is strictly greater than 0, we have limit of x n upon y n is equals to L. Then we must have limit x n is equals to plus infinity if and only if limit of y n is equals to plus infinity. I repeat the statement given as, we have two sequences x is equals to x n and y is equals to y n of positive real numbers r, and we have L belongs to R with L is strictly greater than 0, and the condition is limit of x n upon y n is equals to L. That means the sequence of x n upon y n, the limit of the sequence of x n upon y n is equals to L. Then in this case, if limit of x n is equals to plus infinity, if and only if limit of yn is equals to plus infinity. That means, if limit of xn is plus infinity, this implies limit of yn is equals to plus infinity, and on the converse part, if limit of yn is plus infinity, then we must have limit of xn is equals to plus infinity. Now, let us start with the proof. As given in the statement, limit of xn upon yn is equals to L. So, there exists a natural number k such that we have this inequality. This inequality states that 1 upon 2 L is strictly less than xn upon yn, and xn upon yn is strictly less than 3 upon 2 L for all natural numbers n greater than or equals to k. I repeat, as given in the statement, the limit of the sequence xn upon yn is equals to L. Then, by the definition of convergence of a sequence of real numbers, we can say that there exists a natural number k such that 1 upon 2 L is less than xn upon yn, and xn upon yn is strictly less than 3 upon 2 times of L, where L is strictly greater than 0 and L belongs to R. For all natural numbers, n is greater than or equals to k. Hence, we have 1 upon 2 times L into yn is less or equals to xn, and xn is strictly less than 3 upon 2 L into yn, as we can check from the previous equation. If we multiply yn both the sides, we get 1 upon 2 L into yn is less or equals to xn, and xn is less than 3 upon 2 L into yn for all natural numbers greater than or equals to k. Recall the previous definition. If we have two sequences, let x is equals to xn and y is equals to yn be two sequences of real numbers r, and suppose x is equals to xn is strictly less than yn and yn is equals to y for all natural numbers n, then we have, if limit of xn is equals to plus infinity, then limit of yn is also equals to plus infinity. I repeat the result. We have a result if x is equals to xn and y is equals to yn be two sequences of real numbers, and suppose that x is equals to xn is less or equals to yn and yn is equals to y for all n belongs to natural number. Then we have, if limit of xn is equals to plus infinity, then we must have limit of yn is equals to plus infinity. So, from above result, we can conclude that limit of xn is equals to plus infinity if and only if limit of yn is equals to plus infinity. Remark: the above conclusion need not hold if either we have L is equals to 0 or L is equals to plus infinity. In today's lecture, we discussed about monotone convergence theorem. We also discussed Cauchy's convergence criteria and properly divergent sequences. In the next lecture, we will discuss some topics related to properly divergent sequences. Thank you.